Hello and welcome once again for another EE324 lecture. This is the 12th lecture. We're going to be discussing transfer functions of linear time invariant systems. So basically everything that we've learned thus far have been linear time invariant systems, but I thought we might better use the terminology. This is usually written as LTI. And all that this means is that the differential equations have constant coefficients, because if it was not constant coefficient, then you would have a function of t that would be put in front of as the coefficients for the differential equation, and obviously then it would not be constant. So constant coefficients means linear time invariant in our systems, because we're always going to be caring about time. And another piece of terminology that I think I may have mentioned before, but I'm going to rehash it, is that we're going to recall that a single input, single output, or SISO system equation looks like, and we called this the I/O. This is what we've been calling the I/O. It looks like AN times, where AN is a constant, right? Because the coefficients are constant, so we're linear time invariant here. AN times x to the n plus AN minus 1 times x to the n minus 1 plus blah, 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 plus A2 times x double dot plus A1 times x dot plus A0 times x. And that's going to be equal to the inputs, right? So the inputs might be a force, F, or they might be some kind of voltage in an electrical system, or whatever that the case may be. But we are going to call them U's. So BM, and by the way, generally N is greater than or equal to M, and it's usually greater than, meaning that you don't usually have as many derivatives in the inputs as you do in the outputs, plus b to bm minus 1 to the times u to the m minus 1 plus all the way down to b0 times u. That's the input-output equations that we've been getting. We've been putting them in this form. And now, what is the transfer function? So the transfer function, we call it h of s. And in your book, although I've seen g of s as well used, it's not a standard notation. So sometimes g of s, right, or something like that. But h of s is equal to the Laplacian transform of the output divided by the Laplacian transform of the input, assuming zero initial conditions. Okay. So we're going to assume all of the initial conditions are set to 0, and we'll see an example of this in a moment. And because of that, so it's like a system that has not had any stored energy in it, right? So we're just interested in the system when there is no stored energy. Okay, so let's take a look at this, and we'll see what the beauty of the transfer function is in a moment. So we've seen equations like this: mx double dot plus bx plus kx is equal to f of t. And if I take the Laplace transform, I'm allowed to pull the constant out, right? So I get m times the Laplace transform of x double dot, and so on. And when I take the Laplace transform, then I have to do this. I have ms squared times x, capital X of s. And if the initial conditions were not 0, then I would have minus s times x of 0. This is the standard way of doing the Laplace transform. Minus x dot of 0, so those are the initial conditions for that, plus bs times x of s minus x0, again that initial condition, plus kx of s, and that's going to be equal to f of s. But again, the initial conditions are going to go to 0 because we're dealing with the transfer function. And what we're going to get is we're going to get x of s, I can factor this out, times ms squared plus bs plus k is equal to f of s, where f of s is the Laplace transform of the input function. Notice that then I can divide by by f of s, which would give me 1 over here, would give me 1 there if I divide through, and then I'm going to divide through by this term, and what I get is x of s divided by f of s is equal to 1 over ms squared plus bs plus k. So there's an important point to be made here, that the transfer function is the same regardless of the input function, right? This is my Laplace transform of the input function, but the transfer function doesn't change because f of s changes. Therefore, the inputs play no role in the transfer function. And as we'll see later, this is convenient because then I can just, if I'm trying to solve these systems using the Laplace transform, I can just plop that thing right back out here. Take the Laplace transform and multiply it there, and it's convenient. So this is just reiterating the transfer function is always the same for a given system. So for this system, it will always have this transfer function. Now, obviously, each system has its own transfer function. Otherwise, we wouldn't have to find them. The roots of the denominator of the transfer function are called poles. This comes from complex analysis, but the basic idea is that the poles are where the transfer function blows up toward becomes indeterminate, if you will, because of the fact that it goes to 0, right? In the denominator. Whenever you have a denominator going to 0, obviously you have a problem. So these are the poles. And in our example, because we had a square, we had a function that's just a quadratic, then the poles are just we can just use the quadratic equation, and obviously we have m and k and b in that, so we're good there. Let's do another example that's slightly more complicated. So let's say I have some massless cart, and it's moving, and so then in its frame is, we're going to call it u, the frame of the massless cart. And then there's a mass sitting on the massless cart that is also attached to a spring and a damper, linear spring and a linear damper. And it's allowed to roll back and forth. And we'll obviously give its coordinates x. We're going to find the transfer function of this system. And in order to do so, of course, we're going to have to draw the free body diagram. We're going to recall, just to reiterate, that the linear damper and the linear spring are restoring. In other words, they always try to put the mass back towards its equilibrium position. That doesn't matter if it's being compressed or it's being stretched. So either way, it's always opposing the motion, right? Always opposing which way x is going. However, because we have the cart u that's also moving, the amount that the spring is either stretched or compressed by really depends on the distance between u and x. So that's why we're going to end up with an x minus u here in my equations. So if I draw the free body diagram, here's the free body diagram. And now I'm going to write the equations. So I get minus FD is obviously mx double dot, so minus mx double dot minus b times x dot minus u dot minus k times x minus u, or I can obviously multiply through by -1 or just add all the terms to the other side, and I get mx double dot plus b times x minus x dot minus u dot plus k times x minus u is equal to 0. Notice that there are no input forces. However, we effectively have something that's like an input force in the sense that the cart is moving. right? And we saw this previously with like the ground moving, right? If the ground is moving, then effectively it acts as an input. So it's the same thing with this nice little cart here. So now I'm going to get it into the input-output equation. That's what I have here. That's the I/O, right? That's the I/O. And from the I/O, it's pretty easy to then write out what the transfer function is. I'm going to skip the part of actually writing out the Laplace transform, all of that, all of those details, and just get right to what we end up with. Notice that we have a b times u dot, so we're going to end up with an s term there. This was with a double dot, so we're going to have an s squared, so on. And remember that we're assuming the initial conditions are 0, so we don't have to worry about those terms. And when I do that, my transfer function for this system is bs plus k divided by ms squared plus bs plus k. So that's my transfer function for this system. And again, it doesn't rely on the inputs at all. So the inputs do not play a role in the transfer function. Only in the solution, though. However, when we go for the solution, we have to multiply by the input function, right? So it does play a role in the solution, but not in the transfer function. How about we do one more example? In this case, we have this circuit, V naught. So it has a constant, not a constant. It has an input potential, V naught. I'm going to call this left loop loop 1, this right loop loop 2. And we're going to jump right in and start building the input-output equations. And then once we get the input-output equations, we'll be able to get the transfer function. So we have the junction law, which says minus I1 plus I2 plus IC is equal to 0. We have the voltage loop law. So for loop 1, that says V naught minus VR1 minus VC is equal to 0. And for loop 2, it says minus VL minus VR2 plus VC, because I'm going up, right? I'm going in the opposite direction I did on the other one, so I must be going also in the opposite direction in terms of voltage, plus VC is equal to 0. And I'm going to rewrite this down here because I want to get this in terms of I2. So I'm going to start with the junction law equation because it already has a term in terms of I2. So basically what this tells me is I have to find IC in terms of I2 and I1 in terms of I2. So let's see if we can go about getting I1 in terms of I2, for instance. So we know that V naught minus I1 R1, right? Because that's the current going across here. So I1 R1 minus, well, VC is, I'm going to leave it as VC at the moment, is equal to 0. So what is VC? Well, VC is equal to, actually, I'm going to rewrite this in a different way. This is IC is equal to CV C dot, right? So if I multiply this, if I take this equation, I take the dot of it, I get V naught dot minus I'm actually going to just move this over here. I'm going to multiply this times C is equal to I1 R1 dot times C minus, plus CVC dot now, because I multiplied through everything by that, and this is just IC, okay? So now I get C V naught dot is equal to C I1 dot, well, let's move all of the terms that are multiplying here. I1 dot plus IC. Okay, so there's my IC. However, that doesn't get rid of my, I wanted to get this in terms of I2, so I'm going to need the other equation as well. And we know that from the other equations, in fact, actually, let's not put this in terms of IC yet, because we might be able to get rid of it by using this. So we also know that VC VC is equal to VL plus VR2, right? So now I can actually substitute that in, so I get C V naught dot equal to C R1 I1 dot plus, this is going to be in terms of I2, so plus C VL dot plus C VR2 dot, right? So I just did this substitution in for CVC dot. And notice that VL dot is going to be in terms of I2, and so is R2. So that's nice, because that's going to be what we wanted. So we're going to get CV naught dot is equal to CR1 I1 dot plus CVL dot is going to be C times I2 double dot times L plus C times R2 times I2, right? Because I2 is the current going, dot, because I forgot I had a dot here, right? So because of that, we can now write this in terms of I1. We can use CR1 I1 dot is equal to CV naught dot minus CLI2 double dot minus CR2 I2 dot, which means that if I put this in differential form, this is going to make my life easier. CR1D I1 is equal to this, and therefore I1 is equal to CV naught dot minus CLI2 double dot minus CR2 I2 dot over CR1D, and I'm just going to cancel out the C's here. Okay? To make my life a little easier. Oh, so this is nice. So now I have I2 minus, right up here I had I1 minus I1, but that's just V naught dot. And if I multiply through the negative sign, it's going to be plus L I2 double dot plus R2 I2 dot divided by R1D. And then finally I have plus IC is equal to 0. So now I have to figure out how to get IC in terms of I2. So I'm going to go back to my equations here. And notice that let's write this down again. VC is equal to VL plus VR2 which means that CVC dot is equal to CVL dot plus CVR2 dot, which means that IC is equal to C Li2 double dot plus C I2 dot times R2. So if I substitute that in for IC, then I get I2 minus V naught dot plus Li2 double dot plus R2 I2 over R1 times D plus CL I2 double dot plus CR2 I2 dot is equal to 0. So this is not my IO equation yet, but I'm going to get it down here and get it into my IO equation. Then is actually I should probably do an intermediate step. So I have to multiply by R1 times D. So that gives me R1 I2 dot minus V naught dot plus Li2 double dot plus R2 I2 plus CL R1 I2 triple dot plus CR1 R2 I2 double dot equal to 0. And if I rearrange, then I'll have it in my IO equation. I'll have CLR1 I2 triple dot plus C R1 R2 plus L I2 double dot plus, because this was double dot, right? Plus R1 I2 dot plus R2 I2 is equal to V naught dot. Okay, and is this thing? That's my IO equation, and now I can just get my input output. I mean my transfer function becomes CLR1 S squared cubed plus CR1 R2 plus L s squared plus r1s plus r2 is equal to s. Oh, and then I should write what these are multiplied by. So this is going to be, I'll call it I, capital I of s. And this will be times, we'll call it capital V of s. Okay, so that means that I of s divided by V of s is going to be equal to s divided by all of this mess. CL R1 s cubed plus C R1 R2 plus L times s squared plus R1 times s plus R2. Okay? And this is my transfer function. All right, that's all that I have for this video. Hope you enjoyed it. See you again soon.